Hi everyone, thanks for joining this talk at Ignite Summit. I'm Ferda Arikan. I work for Cardano Risk Management. I'll be talking about how we built our quantitative analytics platform using Apache Ignite. Cardano is a privately owned, purpose-built risk and investment specialist founded in 2000. We do things differently and we challenge the status quo. If you would like to find more about what we do, you can visit our website at www.cardano.com. Cardano Quantitative Analytics is the methodology hub for Cardano. Our focus is mainly on pricing and risk management of financial instruments and their derivatives. The team's daily tasks are split across two areas, working on pricing and hedging methodology, and also providing quantitative consultancy both internally and externally, mainly involving ad hoc analysis of trades or new instruments or hedging problems. So for those who don't know, quantitative analytics involves using mathematical models to solve financial problems. Quantitative analytics team as a primary product develops models, and they are eventually implemented in our analytics library called Quantum. The library is highly configurable and modular. We have instrument models explicitly and pricing engines separately from instruments. We have market data dependencies explicitly modeled. So if you would like to perform a calculation, you can first get a shopping list of market data items that you need to perform that particular calculation. Once you have that market data, you can then perform the calculations. Delivery of this library is done through multiple channels, such as an Excel add-in, Python package, and software libraries for direct programmatic access. Eventually, our code runs in user's execution domain, and as a provider, we can't control that domain. Difficult to optimize for multiple environments. We have a wide range of users that need to perform certain calculations, business users analyzing trades or portfolios, engineering teams developing in-house software or building data pipelines or batch processes. On the chart, you can see some of the technologies that are commonly used by different teams. So there's a huge variety of access methods. So what's the challenge? How do we make analytics available to all users in a performant and scalable way? There are different types of users performing trading and hedging decisions, portfolio analysis and monitoring, as well as client reporting. Each use case has different performance requirements. For trading, calculations should finish in a blink. For batch processes, one can argue it is okay if you finish before sunrise, but this is often a misconception. Batch processes are actually where your scale will be tested. You would be scaling the overheads that is hidden in your code as well. So you should still be quite efficient on how you run your calculations. The system should be able to deal with adding new asset types and market data, as well as a significant increase in user requests. We aren't talking about increasing the number of users, but because of programmatic access, users may make quite large calculation requests. Let's look at a generic portfolio analysis example. They are often performed using scenario analysis. Each instrument is then revalued given a scenario that applies to a number of risk factors. If you have small values for each of these parameters, it's not an issue. But then you may have large scenarios and bigger number of days and a lot more assets. You may end up quite quickly with a quite large number of computations you need to carry on. Also, multiple analysts may be performing other similar analysis. So this could be one analysis doing a 10 scenario, 10-day, 1,000 asset simulation, and then you could have many of those. If we look at how this is set up in the wider industry, traditionally, well, separate teams develop models, libraries, and eventually the code that consumes those models. Once a model is developed, either same team or a different team turns that into a software, and later on that software is adapted to be part of a wider infrastructure. At the end, we may get some feedback. Often that feedback does not reach to where it would be most useful at the right time. And generally, that feedback might be related with the integration layer. The code generally is well isolated and ring-fenced. Nobody wants to look inside that code, and then this is because that's also the code is deployed to an external platform, and there should be a good isolation to make sure that other processes are not affected. But how can we turn this process inside out so we can control to runtime as well? When we think about centralized approaches, web services come to mind. We then automatically start to talk about web services. They have many benefits, but how do they scale? We need to look into that a little bit more. Well, let's remember a famous quote: give me a load balancer capable enough, I shall scale the world. Well, it's not a real quote, I made that up, but this is almost seen this way. If I put a load balancer, if I deal with the traffic, I then am also dealing with the scalability of my application. For some types of applications, especially if scaling means taking a vertical slice of your stack, this may be just the right strategy. But for some other type of applications, this may not be the optimal strategy. But how do you share also context? What about common objects and data, fault tolerance, computation guarantees? Surely we can improve all of that. Maybe let's have a design session. We can create a layered architecture with web services and handle client requests, then deal with data, then pass on to the execution layer. That could as well be an RPC framework or a distributed runners that execute your code and then return the results. But how do you share data? It's easy, it's not too hard, right? You can use an in-memory database. Most web applications actually use them and share session data, user data, and we can plug in an IMDb. We can also add the custom code around it to make sure that it works correctly with our application. But then how do we know what's going on around us, right? There are many runners doing same or similar stuff. There needs to be a notification mechanism to provide some sort of asynchronous behavior. Then we can add a messaging service and also some more custom code around it. We now have some system that can share messages, share data, execute computations, handle data in different layers. But who runs this show? It may as well be quite chaotic if there is no coordination. Then we add a coordinator to get the nodes to work together. If we add the coordinator, we now unlocked an achievement. And we have to manage all of this infrastructure because we added quite some extra systems and also quite some services doing different stuff. Some institutions can do this if they have the will and resources to manage this kind of architectures. It's perfectly fine. Some even created their own DSLs or RPC frameworks, but you also need to maintain all these systems and all the custom code that happens along the way. If we look at our approach, we call it analytics for all. This is achieved by creating an easy to use and maintain a scalable and performant system. We have a lightweight web service as front end. By front end, what I mean is an entry point to our system that users can pass their requests. And Apache Ignite as a in-memory database, compute grid, and messaging. If we roll the credits, probably Apache Ignite will fill all the roles. We also have a separate application that tracks the cluster metrics and health. Also a user interface that provides more transparency to the cache data. So we can see what's inside the cluster data, what's going on, we can monitor, and then all this works nicely by using almost all built-in Apache Ignite features. If you look at each layer a bit closely, public API is GraphQL, so it's easy to learn. It's basically for those who don't know what that is. It's a query language for REST services. It's easy to learn, schema-based, and it has a type system. There are lots of client tooling and libraries are available, suitable for all use cases we have. It is basically any device or code that is capable of making a web call can run our calculations. That's the benefit. If we look at the next layer, data cache and storage, we use scheduled data loads. We have a scheduler that loads the data from the data source at given frequencies. To run the scheduler, we use a cluster singleton service. For us, all of our nodes are server nodes. We don't differentiate between the functionality of the nodes. So when we need to run such a service once, then it automatically becomes a cluster singleton for us. We use replicated caches. All the data is available on every node. At the moment, we don't have a huge scale data, therefore we can do this, and this allows us to run any calculation anywhere. We don't need to differentiate between the nodes. Later, we will revisit this strategy. As the data grows, there will be better alternatives. We use Ignite persistence that allows us to be protected against crashes, restarts, reboots. We don't need to repopulate the cache. Ignite persistence takes care of this. Data streamer also makes big difference. When we populate the cache, we use streamer to insert entries in bulk. One thing I would like to mention is that the scheduled load allows us to reduce the amount of data we need to transfer, because now we can compress the common data points, and this provides huge efficiencies. We track a time window of historic data, and then some data is required for curves, some data is needed as fixings, but then there will be overlap, and we cancel all the overlaps and just request the remaining data from the data source. Below you can see our data retrieval logic, which is used everywhere in the application. Some of the steps are performed by the developers. Some of the steps are built-in Ignite functionality. Putting all together gives us this nice filter mechanism, which allows us to only go to the data source for the missing data points. So we first check if the data is prefetched. This is limited to a compute function or a current scope, so data may already be locally available. If that's not the case, we then use getAll API to retrieve all the data. Then Ignite deals with the next two steps. It loads it from memory, or if it's not available in the memory, loads it from the persistence. If it's not even available in the persistence, then we need to go to data source and retrieve it from the source and store it in the cache, and it is available for every computation requests later on. As part of our storage strategy, we have an algorithm that specifies the expiry of each cache entry. So we have our own expiry policy implementation and store this on cache entries. Every data point has an expiry associated with its age. older data expires slower than more recent data. So this may sound a bit counterintuitive, but we see that more recent data may be less stable, more volatile, and older data is more established, less subject to change or corrections. Then for us, older data gets refreshed less frequently than the more recent data. And expired data gets explicitly removed or refreshed. If we move on to next, data cache and storage strategy, we have an on-demand data load. This is another data load strategy. This happens during a compute request. If the data load logic that we looked at earlier concludes that data should be retrieved from the data source, we retrieve it and store it in the cache. But then to perform this more efficiently, we inspect all the requests we received from the user, handle all together as a separate job, such that we can also benefit from compression, so that any single data point is only requested once from the data source if it's not available in our cache. And then once we solve the data requirements problem, we move on to the next stage, compute strategy. We allow at the moment computations to be performed on any node. At the moment, this is an efficient strategy. As the data and type of instruments grow, which also will mean that the type of objects we will build will grow, we will look into different strategies. All calculations are inspected and grouped by likeness. This is a concept we defined. We use some parameters to group together computations that we know will unlock huge efficiencies. This both ensures each compute job uses data efficiently and also makes best use of the analytics library, as you can unlock further efficiencies. Monitoring. How do we monitor all of this then? In a way, we don't monitor. It's all automated with some self-maintenance and alerting provided by us. We have created a simple application called Goldeneye that monitors all the metrics that we want to track and alerts us when something goes wrong with the system. Here you can see a small part of the application, but this is only a byproduct. All the monitoring and alerting is automated, but we thought while we have the data, we can as well put some fancy charts. We would like to glance every now and then to see what's going on. So we have few other pages that gives us more metrics, but actually we use very little amount of the available metrics in the Ignite framework. And SQL support makes all of this rather easy and also possible. By just running SQL queries, we can learn a lot about the cluster, and this dashboard is an example. We can track memory usage, CPU usage, job statistics, threads, thread counts, duration taken, wait time, waiting jobs, executing jobs, and so on. We could also look at cache contents, amount of data, and its evolution as well. Let's briefly talk about our deployment model. Well, we use Jenkins to build and test our software. Once everything goes well, containers are, or maybe images are pushed to our private container registry. Octopus deployed and deploys our workload to Rancher environment for dev, QAT, and production. Something we did specifically for Ignite is to make sure that we synchronize liveness, readiness, and cluster active. If you are using Kubernetes, you may know that liveness and readiness are the health endpoints. Liveness says that, okay, pod is running, it is alive. Readiness says, okay, it is ready to receive traffic. We actively use them and we synchronize readiness with the cluster active. So until actually a node joins the cluster, and is active, we don't want any traffic to be routed to that node. So we mark those nodes as not ready, and they stay that way until they join the cluster. If a node gets an error when joining the cluster, we mark the node to perform a cleaning at startup. So at next startup, it performs self-maintenance and joins the cluster without any issues. This is possible because, well, what can go wrong in our environment? Okay, we have Ignite. Ignite runs in a read-only container, so nothing can change there. We have in-memory data, but at startup, there is nothing in the memory. And then we have the persistence. That's the only moving part for us. And if something goes wrong, we generally just remove the persistence of that specific node. When it joins, it runs the rebalancing, gets all the data automatically, and then it's ready to serve the requests. So that's rather convenient for us. The highlights for us is we can further adapt our library to the run environment, because now we can develop our library against a known environment, or we can actually get them to work together. We have a platform where we can easily adapt to changing requirements as well. We can add more data, more instruments, more CPU, more RAM. It's rather easy to scale whichever direction we want to scale. Benefit from first-hand optimizations. We can unlock all potential performance. This is coming from both our library and the execution platform. Conclusion is, well, we created a scalable and performant analytics platform. We can serve all users from same platform with uniform functionality. We removed all major bottlenecks, which is data access and hardware limitations. These aren't specific to us, but then these are general problems for any application that may need to scale or increase its capabilities. But now we removed them using Apache Ignite. Data access is 10 times faster than the alternatives we have. This is quite rapid, and we can actually work against a known database as well. Because in Ignite, we model the data in a way that it is compatible with our library rather than an external system. Computations have huge potential to be further speeded up as well, because we can further now break down our computations, cache intermediary objects, cache further objects, and then further speed up all the calculations. That's it from me. Thank you very much for listening to this talk. If you have any questions, I'll do my best to answer. Thank you.
Ferda, thank you for that.
Thank you, everyone.
And welcome back to the stage. We have a couple of questions. The first one is about the cache. So how do you know what is in the cache in your application, and how transparent is it?
I see. Okay. Well, this is quite critical for us because we make calculations, financial calculations, and we need to be able to audit the data and see every timestamp when the data was retrieved. We built a simple application that allows us to be able to browse every entry in the cache. This is all possible via the SQL API that makes it super easy, really. So we just run SQL queries to inspect and look at the data if there's a need or if there's a question. So that provides extra confidence to the users as well, because if the cache is a black box and you can't explain what's going on there, and if there's a problem, then it's quite difficult to debug and chase that. So that, yeah, SQL API allows us to do that easily.
Okay, excellent. Another question. How do you access local resources while the application is in the cloud?
Well, we don't have many local, some of the data has to stay on our private networks. We can't deploy them. We don't have many of those, but we created a file system abstraction using Ignite messaging, and a WebSocket technology, so we can actually get Ignite to request resources from our private network as well.
Okay. Finally, the last question. What's the differentiating factor in your implementation from a generic web service?
Well, in a way, our entry point is a web service, and you can say it's a generic web service, but the power comes from the ability to be able to first, we can scale the data, we can easily change our data strategy, we can easily switch to, for example, we will add more instruments to the system, our data will grow significantly, then we will move to, for example, partitioned data. If we had an external database with working with a web service, that would have been quite challenging. It's a major change. Also, we can change the number of nodes, scale it up quickly, and distribute the computation. So it's quite different. Just the entry point is a web service, I would say. So, yeah.
Okay. There's another question just come in from Damon, who says, I think you said you can add nodes easily, which sounds important. Does that slow the cluster down much while data is moving to new nodes?
We didn't notice any slowness when we added. Well, we use Rancher. Rancher is kind of an extra layer, orchestrator layer over Kubernetes, and we can easily, by just clicking a button, literally add nodes, and then this is of course limited with the availability of the workers, but Ignite does everything else. Really, data is rebalanced, loaded to the new node. Once it gets all the data, it joins the cluster as well. Then we can distribute the jobs, start sending traffic as well. So it can receive traffic from the GraphQL, also jobs from the other nodes.
Great. Okay.
Maybe one bit, sorry to interrupt. How much while data is moving to the new nodes? I didn't measure this, but we don't have a huge data set at the moment. So given current strategy, it doesn't take long. Sorry.
Do you expect the data set to increase vastly?
Yes. We will add more instruments which require huge amounts of data.